You ever just stop and think about the magic that's happening literally every second when you make a call, stream a show? I mean, information is on this wild journey. And today, we're going to follow that path all the way from a simple sound wave to a complex digital signal. Let's get into it.
So it really boils down to this question. How does your voice, just a vibration in the air, how does that travel across the world instantly and sound perfect on the other side? It feels like it shouldn't be possible, right? But it all starts with one single thing.
Right here, this is the starting line, a smooth, continuous analog wave. Just think of it like the raw, unfiltered data of the real world. Your voice, the colors in a photo, you name it. It's full of detail. But here's the catch. Our digital gadgets, they don't speak this language. So to translate it, we need a recipe. And that recipe, well, it's a simple 3-step process for turning these waves into the language that computers do understand, ones and zeros. Seriously, this is the bedrock of pretty much all digital communication.
Okay, so the official name for this process is pulse code modulation, or PCM for short. And you know what? It's actually a really elegant 3-part system: sampling, quantizing, and encoding. Let's break down what each of those really means. All right, step 1, sampling. The best way to think about this is like you have a super fast camera and you're taking thousands of snapshots of that analog wave every single second. Each snapshot just measures the height, or what we call the amplitude of the wave at that exact instant. And yeah, the more snapshots we take, the better the final picture is. Okay, next up, quantizing. See, the problem is those snapshots could have an infinite number of different heights. We can't work with that. So we simplify. We take the measurement from each snapshot and we just round it to the nearest pre-approved level. It's kind of like rounding 2.9 up to 3. It's an approximation, sure, but it's a really, really good one. And the final step, we encode. Now that we have these nice rounded levels, each one gets its own unique binary code, a string of ones and zeros. So level 5 might become 101, level 2 becomes 010, and boom. Just like that, our smooth flowing wave has been perfectly translated into a clean stream of digital bits. And here you have it, the whole process in one shot. You see the original wave, you see the little sample points we took, how they snap to those quantized levels, and then bam, the final binary sequence. We've gone from a continuous analog signal to a discrete digital code. It's officially ready for its big journey. But, this is where things get tricky. Sending this digital code isn't as simple as just putting it in an envelope. The real world, the actual physical stuff it has to travel through, it messes things up. So in a perfect world, our ones and zeros would be these beautiful, clean, sharp pulses. But we don't live in a perfect world. As that signal zips through a cable or flies through the air, it gets smeared out. It gets distorted. It ends up looking, well, a lot messier. And this smearing effect, it actually has a name: inter-symbol interference, or ISI. It's what happens when the energy from one pulse kind of spills over and bleeds into the one right next to it. And this is the #1 villain we have to fight in digital communications. This picture shows you the problem perfectly. Think about any channel, a wire, the air, whatever, as having a kind of physical speed limit. It just can't switch from on to off in 0 time. So when we try to send a perfect, sharp pulse into it, the channel literally can't keep up with those sharp edges. And what comes out the other side? A distorted, ringing mess that drags on way longer than it should. And what happens when you send a whole bunch of these pulses, one after another? Well, you get chaos. Each pulse just blurs right into the next. It's just like someone slurring their words together. The poor receiver at the other end is trying to read the signal, but it's getting all this noise from its neighbors, and that leads to mistakes. A 1 starts to look like a 0 looks like a 1, and everything falls apart. So here's the real kicker. This signal smearing, this ISI, it gets worse and worse the faster we try to send our data. And let's be honest, we always want to go faster. This creates a huge problem. How do we crank up the speed without turning our data into a complete jumbled mess? This is what we call the bandwidth crunch. Yeah, the key thing to remember here is that every channel has a fixed capacity. Just think of it like a highway. Your bandwidth is how many lanes you have. There is a hard physical limit to how much traffic can flow at any one time. So, with our insane, exploding demand for everything from 4K streaming to constant video calls, how do we solve this puzzle? How do engineers pull off the magic trick of squeezing more and more information into the same old crowded highway? Well, the solution is just incredibly clever. Instead of trying to just shove more cars onto the highway faster and causing massive traffic jams, we make each car we send smarter.
Here's the best way to think about it. The basic old-school way of sending digital data is like sending a message one single letter at a time. It works, but it's slow. So the big idea was, what if instead of sending single letters, we could send entire words all at once? And that word we're talking about? In our world, we call that a symbol. A symbol is just one unique state of our signal that stands for a whole group of bits. We're moving beyond a simple on or off language and creating a much, much richer vocabulary. This whole technique is called M-Mary modulation, and that M just stands for the number of unique symbols we're using. So how do we create these symbols? Well, we can play with two key properties of our wave. Its amplitude, that's its power or height, and its phase, which is basically its starting point in a cycle. By tweaking these, we can create a whole set of unique signals. Okay, this is where it all clicks. Look at the left. That's the old way. One pulse is either a 1 or a 0. It carries exactly one bit of info. Now look at the right. That's a map for what's called an 8 PSK signal. Each one of those 8 dots is a unique symbol, and each one represents a different combination of 3 bits. Just like that, we've tripled our data rate without having to send our pulses any faster and create more of that nasty interference. And this map has a name too. It's called a constellation diagram. It's basically a picture of our symbol library. The receiver on the other end just has to figure out which dot on the map was sent, and it instantly knows which group of bits it represents. It is a beautiful and super efficient way to visualize all this complex data. But hey, why stop there, right? What if we start changing both the phase and the amplitude at the same time? Well, that's exactly what quadrature amplitude modulation, or QAM, does. Check out this map for 16 QAM. We now have 16 unique symbols, and guess what? Each one of those represents a group of 4 bits. We've just quadrupled our data efficiency compared to where we started. Incredible! You know, this isn't just some abstract theory. This is the engine that's running inside your phone right now. It's what powers your Wi-Fi, 5G, pretty much the entire global network. The ability to create these super dense, super efficient information maps is what makes our modern connected world even possible. And that kind of leaves you with a really cool question to think about. As our hunger for data just keeps growing, what new, even more mind-blowing maps of information will we come up with next?